So we're going to look at comparing ionic bond strength between two or more ionic compounds. And rather than having to look up lattice energies or use the Born-Haber cycle, as we did in the previous lecture, to calculate the lattice energy and then do some comparison, we're going to be able to do this just kind of by looking at the formula, looking at the structure of the compound. And the way we're going to do this is using something known as Coulomb's law. Now, this will be, again, another concept I'm going to dive a lot deeper into later. But for right now, suffice it to say, think of Coulomb's law as just opposites attract. Opposite charges attract, and the stronger the attraction is between them, the stronger the bond is going to form. And there is a numerical way, or there's a formula for Coulomb's law. We're not going to use it to do any calculatings right now, but we're going to use it to make our comparisons. The energy of a bond is equal to some constant. Don't worry about this. Times the charge of one ion. I should say the product of the charges of the two ions, Q1 and Q2. That's not a 9, that's a Q. And all of this is over the radius between the ions. So Q1 and Q2 are the charges of the ions. So +1, -2, +2, -2, whatever the charges are on your ions. And because that's on the top part of a fraction, what that means is the larger the charge, the more the attraction. And R down here is the distance between the two ions, or the distance, the radius between the two nuclei of the ions. You can just think of this as the distance between two charges. Now, because it's at the bottom of a fraction, the smaller that number is, the larger the attraction. So the closer the charges, there's more attraction. Farther away, there's less attraction. Now, again, I'm not going to have you do any calculations yet, down the road probably, but for this unit, all we're going to do is make some comparisons. So let's compare lithium chloride to cesium chloride. And the question is, well, which one has the stronger bond? So first thing we're going to do is compare charges. Okay, so look at your periodic table. See that lithium's in the first column. Lithium will have a +1 charge. Chlorine is a halogen, always has a -1 charge. And then look at cesium. Well, cesium is +1, chlorine's -1. So same charges. What does that mean? That means there's going to be no difference in the top term of Coulomb's law. That Q1 times Q2 is the same for both lithium chloride and cesium chloride. But there is a difference in the radius. Again, look at your periodic table. You'll see that lithium is almost as at the top of the column, just about. Cesium's farther down. What is the periodic trend for size as you go down a column? Well, lithium is smaller and cesium is bigger. So that's lithium, this is Cl, this is cesium, that's Cl. And this distance here is smaller than that distance there. So the cesium cation is bigger than the lithium cation. How do I know that? That's the periodic trend. The result of that is the charges in lithium chloride are closer and will have the higher lattice energy. In fact, if we look at the formal numbers, I don't want you to memorize these numbers. I'm using this just to compare. The lattice energy for lithium chloride is negative 834 kilojoules per mole. And for cesium chloride, it's negative 657 kilojoules per mole. Now you say, well, wait a second, my math, a bigger negative number, that's smaller, right? Not in chemistry terms. Kind of look at it in terms of absolute value. Lithium chloride is releasing more energy when it forms, and so it's a lot more stable because that's a lot stronger of a bond. So don't look at it, you have to look at it in terms of like absolute value of those numbers. Now let's look at a second example. Let's compare sodium fluoride to calcium oxide. So again, the first place you want to start is charge. And I'll explain why in a little bit. Sodium is in the first column, it's +1. Fluoride is a halogen, always -1. Calcium is in the second column, and oxygen is always -2. So calcium oxide has larger charges, both of them are 2, so it's going to have the stronger ionic bond. I don't need to worry about size. And let me show you why you always start with comparing charges first. The lattice energy for sodium fluoride is negative 910 kilojoules per mole. For calcium oxide, that's like negative 3,400 kilojoules per mole. So the reason we always start comparing charges first is that charge has a much bigger effect. Just compare those values. So if you come up against a problem where there's a difference in charge and a difference in size, go based off of charge. So you always start with charge first. If the charges are equal, like in our first example, then you compare size. If the charges aren't equal, then that's where you stop. You just compare which, charges are bigger, and that's where you stop. Now, last thing I want to cover in this series of lectures is looking at polyatomic ions. Now, every ion we've looked at so far has just been what I'd call monoatomic, meaning there's one atom involved, like a sodium ion or a fluoride ion or so on. But there are ions exist that are made up of multiple atoms. And we're going to look at the structures of these later in the chapter. But polyatomic ions are ions comprised of more than one atom, hence the prefix poly. And we will look at the structure of these later. Now, these are going to be very common in GChem. And so I need you to memorize these. And what I mean by that is no name, formula, and charge. A little bit later, I'm going to add structure to that list. So we kind of start at the top of the list here with ammonium. Ammonium is NH4 with a plus charge. And that plus charge is on the nitrogen. I know it's kind of drawn out to the side there, but it's actually the plus charge is on the nitrogen. And then hydronium. Hydronium H3O plus, the plus charge there is on the oxygen. All right, don't worry about peroxide. Let's cross that off the list. Same thing with azide down here. But hydroxide, OH minus, the negative charge is on the oxygen. Acetate is CH3COO minus. That minus charge is there on that oxygen. You might see that drawn like this sometimes. Know both ways because you'll see them interchangeably. Cyanide, CN minus. The negative charge is on the carbon. Oh, no, we'll put X there, but just kind of remember that the negative charge is on the carbon. Then we come to a couple of closely related ions, carbonate and bicarbonate. The difference between them is carbonate is CO3 minus 2. Bicarbonate has that hydrogen on there and a charge of -1. Now, the next two ions illustrate kind of a naming trend. Notice that nitrate and nitrite only differ by one oxygen atom. Nitrate is NO3, nitrite is NO2. And I want to point this out because that highlights something important to note in terms of naming. A suffix of ATE refers to a higher number of oxygens, and ITE refers to a lower number of oxygens. They both have the same charge, just a different number of oxygens. Now we see the same thing with sulfate. Just kind of look at sulfate and then go down to sulfite. The difference between sulfate and sulfite, same charge, different number of oxygens. Now, if you throw a hydrogen onto sulfate, it becomes hydrogen sulfate. HSO4 with a charge of -1. You might also see that called bisulfate. And then hydrogen sulfite has an extra hydrogen on there. Again, you might see it called bisulfite. Now, there's a series of phosphates that you should know. Again, just depends on if there's hydrogens or not. Phosphate is PO4, 4 oxygens, -3 charge. Hydrogen phosphate is still 4 oxygens, but with a hydrogen on there, and the charge goes down. Dihydrogen phosphate, there's 2 hydrogens on there, and notice what happened to the charge again. Now the next 4 are kind of interesting because they have the chlorate and the chlorite trend. Again, deals with the number of oxygens. But this one, we can go even further in both directions. We can have even more oxygens, ClO4, and that has the prefix per. That prefix per kind of adds more oxygens. And then notice down here, ClO, 1 oxygen. we use the prefix hypo to represent even fewer oxygens than chlorite. So the only difference between these four polyatomic ions, they all have the same charge. It's the number of oxygens that's different. Then we have chromate, CrO4 minus 2. Dichromate has the same charge, slightly different number of atoms, Cr2O7. And then permanganate, MnO4 minus. So as I said before, I need you to memorize all of these. Name, charge, formula, and it might even be helpful to make um, index cards out of them. Make some flashcards and start memorizing these now.